I'm going to cover the third set of this series. I'm going through the through a Calculus 2 midterm exam. And for the previous video, I covered problems 4 through 6. Now I'm going to cover 7 through 9. For this particular problem, the key is you need to know the monotonic convergent theorem definition before proceeding. It states the monotonic convergent theorem cannot be applied to the sequence n inverse tan n from 1 to n equals 1 to infinity because, so there's two things. We need to know what this represents as a function, and we need to know what the definition of the monotonic convergent theorem states. So the monotonic convergent theorem, so monotonic convergent theorem. So basically there's two pathways. So if a function increases absolutely and is bounded above the function converges to the upper bound. And then vice versa, you know, if a function is decreases absolutely, and then we keep going, and as we know, if it's bounded below, so we just continue. If the function is decreases absolutely and is bounded below the function converges to the lower bound. So using these two key pieces, what we can do is now we need to understand what S of n equals to. So we have n tan inverse n, and then n equals 1 to infinity. So when we represent tangents, we're going to start with why is this tangent n? So notice how this represents, we can represent this as sine n over cosine. So anytime we notice if we draw the unit circle, there's 4 quadrants. So the key is that we can't have the denominator equal to 0. So cosine, we know pi halves equals 0. Cosine 3 pi halves also equals 0. So as we can't hit the top or the bottom. As we keep traveling along the circle, we cannot hit these two endpoints, but we can hit these two endpoints but essentially we know that sine is 0 here. So at here and here, sine is 0, but this explodes to infinity. So in tangent, what we have is if we have, like, let's say we're taking negative pi halves. So we're going from negative in this direction. For instance, if we go in this direction right here, we can go, this will be negative pi halves. And then if we go in this direction right here, this will be pi halves. So we can't have these cases. So we draw a line, a discontinuity exists. And we notice that in this quadrant, so as we're going from 0, which is 0, to negative pi halves, notice how this is the y-axis, this is the x-axis. So in this region, we know a few things. X equals positive, y equals negative. It's a negative y. And then when we're going from 0 to pi halves, we notice a few things. So x equals positive, y equals positive. So therefore, this from 0, negative pi halves to 0, we're going negative infinity. And then it hits 0 here because sine's 0, so basically it goes like this. Okay. So now the key is anytime you define an inverse function, you're changing x. So x and y are switched when taking inverse. So now you define another axis. So we're switching, like this becomes like, it was like the y-axis and, x. And then we have, right here, we have pi halves. And then right here, we have negative pi halves. And notice how we got multiple discontinuities here. So like if we have pi halves and then we do pi and 3 pi halves, we also have, another function. I believe it's something like, but the key here is we have to constrain the inverse function. Anytime you take an inverse, it has to be definable points. So what we do naturally is we constrain it. So this would be 0, and I believe it goes like something like this. So this is like we basically like flipped it. So essentially we flipped it, and now it's going, this is tan inverse. But in this case we're using the n-axis. For instance, like this would be like the n-axis. For instance, when we're taking the inverse, but this is the inverse function, how it behaves. Notice how there's an upper bound and we have a lower bound. So the upper bound equals pi halves, and the lower bound and notice how the function, if it starts all the way over here, it's always increasing. It's monotonic increasing if we're going in this direction, as from negative infinity to infinity. Tan inverse n is monotonic, meaning it's always increasing. It doesn't decrease at any point, so it just keeps going up, and therefore monotonic. And bounded. Or bounded. It's bounded from negative pi halves to pi halves. So therefore we conclude it satisfies monotonic convergent theorem. Because as n goes to infinity, it converges to pi halves. So this function, we know that this satisfies by itself the tan negative 1, because we know as like n tends to infinity, tan negative 1n tends to pi halves. As n tends to negative infinity, tan negative 1n tends to the other direction, negative pi halves. So we get closer and closer to negative pi halves in that direction. We get closer and closer to pi halves. But now we have S of n is n tan inverse n. So the key here is we know the maximum of tan inverse n equals pi halves. This is yes, as n tends to infinity. But the maximum n, equals infinity. So therefore, if we're multiplying, because the function n is a linear function that keeps going, it's monotonic increasing, so therefore they're both monotonic increasing, or monotonic, but it's always going on towards infinity. So therefore this is going to explode. It's going to take the tan, once we multiply by n, you're multiplying infinity by pi halves, well that's infinity. So therefore so we know the sequence is not bounded. But is it monotonic? Well, n is monotonic. And tan negative 1n is monotonic. Therefore, both are monotonic. Or I would just say, therefore, n tan negative 1n is monotonic. Because you're just taking two monotonic increasing, adding them together. So it just says not monotonic. Well, it is. So the sequence is not monotonic, but the sequence says no. The sequence is not bounded, but the sequence is monotonic. That seems reasonable. Okay, the sequence is not bounded, which we know, and the sequence has some negative terms. Well, it's not. I mean, yes, but we're relating it to the definition. It says the sequence is bounded and monotonic. Well, it's not bounded. And so C basically, so we know it's not bounded, but it is monotonic. So the reason is, you know, it needs to have a bound. It's not constrained within a bound. Therefore, we cannot use a monotonic convergent theorem because it states, yes, it's monotonic, but there exists a bound. And yes, this is monotonic, but there does not exist a bound. So that's where it collapses. And that's the key right there. Okay, for A, it says, what is the largest set of values R such that the sequence limit n equals infinity R to the n converges? Okay, so we have the limits. Okay. Okay, so the key here, this is a function of n. So if we take like a number line, let's constrain it to -1, and we take 1 over here. And this is the R. We're basically taking let this represent R. And then we're going to apply to the n power. Notice, -1 to the n power. Okay, so the big key here is -1 -1 to the n oscillates. So basically right here, if n equals 1, well, we get -1. N equals 2, we get 1. N equals 3, you know, back to -1. So this keeps oscillating between -1 and 1. So therefore, it's not really going to ever hit anywhere. Absolutely. And then 1 to the n equals a 1. So we take 1 to the n. So this equals to, because n starts at n tends to infinity. So 1, 2, 3, so forth equals to 1 for all n. So that's key. And so the same thing, if you take any negative number, so like if we take, let's say 0, and within this range, within that range, we notice that this function, it's going to oscillate. So what's going to happen is we know if we take a fraction, any value less than between 0 and -1, and we're taking it to an n. So if we take the value, let's say 1 over, let's just say 1 over x to the n, x is greater than 1. So this is like, you know, if you take 1/2 to the n, Well, 1/2 to the 1, you start at 1/2 and you're approaching 0. You know, so basically it's and now if you take negative 1/2, so of course we start with negative 1/2. But then we go positive once we square it. We get to some value less than here. And then it becomes negative again when we cube it, gets some value even smaller. So basically what you start here, and then you go to here, and you go here, you go here. And essentially keeps oscillating between, but it converges to 0. And that makes sense because as n gets larger, it gets much, much smaller. But it doesn't follow for negative 1. If you do any fraction in between 0, but if you take negative 1 to the n, what you end up finding is you got 1 and you got negative 1. Well, it's always going to oscillate between negative 1 and the n equals 1. For instance, this is n-axis. Back to negative 1, back to 1, back to negative 1, back to 1, back to negative 1. So it never converges, it never gets smaller. But once you add it so close to negative 1, make it a small fraction like 0.9999 negative, and you take this to the n, it takes a long time to get to 0, but it still oscillates, gets smaller and smaller and smaller. You know, it may seem like this. So you start with like, you know, negative 1, you get kind of close to that, and you go here, kind of seems like it, but as you zoom, you know, it eventually goes smaller, and you know, as you keep going, as n tends to infinity, approaches 0. So the key thing here is we have to exclude this. It's not included in what this said, but anything between that will converge. And then of course if you take 1 to the n, you know, now we're taking positive 1 to the n. Well, it's just always 1 for all n. It's just a flat line. It doesn't oscillate, but it basically, you know, it's always the same. So essentially, the limits, of course, equals to 1. So the limit as n tends to infinity of 1 over, well, it's 1 to the n, well, it's just 1. So it has that limit, but if you take, you know, limit as n tends to infinity, negative 1 to the n does not exist because there's 2, negative 1 and 1. So essentially right here, it's just going to be negative 1 is less, but less than equal. So it's going to be a. So it includes everywhere except negative 1. And that's the key. And it will converge for all those cases. Okay, so now this is an interesting problem. Let me get a new set. Okay, so it says in great detail, okay, evaluate the following integral using repeated integration by parts, and do not use trigonometric formula and or trigonometric method of integration. Do not use tabular method. Okay, so we have this cosine 3x, cosine 5x dx, indefinite integral. Cosine 3x, cosine. Okay, so the key here, we're using integration by parts. So we're going to use the you have the uv minus integral v du equals integral. So let this be equal to the integral. So we're going to start with that assumption, or we defined it. So now we're just going to let u cosine 3x. And we know that du equals, now this is negative 3 sine 3x. We used the chain rule, so we took the derivative of cosine, which was negative cosine 3x, times the derivative of the inner term, which is derivative of 3x, which was 3. But since the derivative of cosine is negative sine, we still have to carry the negative. So now we're going to let dv equals to cosine 5x. So therefore dx. So therefore v is the integral of cosine 5x dx. So what we know is if we have, like, let's say sine, sine x, how would I do sine x prime, we know goes to cosine x. So if we take the derivative, and then this direction is the integral. So we have the cosine term. We take the integral, we're back to sine. But in this case, we're dividing. So therefore, v is actually going to be 1 over 5. You do the opposite inverse of, and then times the sine 5x. I believe I have that correct. So now we're just going to take uv minus v du. So u is cosine 3x. And then v is times 1/5 sine 5x. Okay. And then we evaluate at the limits. And then we do minus v du. So we have v, which was the 1/5. So you have minus 1/5, but du was 3. Minus 3, so minus 3. So this becomes a plus 3/5. We're just taking that out. I took the 3 right here, the minus 3 times the 1/5. And then this is sine 3x, sine 5x dx. I believe that's sine 3x. Okay, sine. Okay, so now we have to do another integration. Okay, so we're going to focus now on this term. And we're now going to use the integration by parts again. So now we're just going to let u2, second one, is sine 3x. So du2 is 3 cosine 3x. So this is supposed to be dx. And then dv2 is going to be sine 5x dx. So this implies that v is the integral of sine 5x dx. So this is going to be 1/5. And then to get to cosine, it's going to be negative cosine 5x right there. So because the derivative of cosine 5x is negative sine, that takes care of that times 5, and they get back to this form sine. So now we have to do it again, uv minus v du. So we have this expression right here. We know that this equals to, so u is sine uv negative 1/5 right here. And then we have cosine 5x. And then we have minus v du. So again, this carries a minus and becomes a plus because we're carrying the minus 1/5 times 3/5. So it's plus 3/5, the integral of cosine 3x, cosine 5x dx. So notice here, we have our original integral that is cosine 3x cosine 5x dx. And now notice here we have cosine 3x cosine 5x dx. So this equals to integral. This whole integral is equal, this term is equal to the integral. So therefore, we're putting it all together. So we're going to put this to, we have the initial term was cosine 3x times 1/5 sine 3x. And then we did plus, okay, now this whole term is plus 3/5, okay, plus 3/5, and now we're going to multiply all the terms together. Now we have negative 1/5 sine 3x cosine 5x, and now we have a plus again 3/5 I. We're calling that an integral because it's equal to the integral. Okay, but we have an integral, and this whole thing equals to the integral. So now we're going to simplify this. So we have 1/5 cosine 3x sine, was that cosine 3x sine 5x plus, or no, this should be minus 3/25, because we're multiplying these two together, sine 3x cosine 5x plus 9/25i equals I. Okay, so now we're going to carry the I to this side, subtract 9/25 from both sides, and we have, of course, this is this 1/5 cosine 3x sine 5x minus 3/25 sine cosine 5x equals to 1 minus 9/25 times I, because we just subtracted. And this equals to 25/25 minus 9/25 times I. And this equals 16/25i, which is just equal to, okay, so that's 16/25. So therefore, wait, hold on a second. Yeah, that should be it. So therefore, the integral is the reciprocal. When you divide, you're dividing both sides, so it becomes 25/16 times the 1/5 cosine 3x sine 5x minus 3/25 sine 3x cosine 5x. And that's it. So basically that's this. You can always simplify more, but this is the key trick. It's more of a trick to solve, and it's just figuring out that you got back to your original term. If we were to keep going, it would add more and more terms. You know, if we had to keep going through, we'd get back to the integral, but it would be a pain just to try to simplify all those terms. So that's where I'm going to stop right here, and see you next time.